In this video, we're going to discuss physical properties and then go over a couple of properties and how they are related to force of attraction, but that'll be in the next short video. So the first thing you recognize is physical property is a result of a force of attraction, and this force of attraction is due to the functional group, the nature of the functional group. And so the properties we'll look at in the next video are boiling point, solubility, vapor pressure. Before we do that, it's useful to have an appreciation for how these physical properties come about. What is it about the functional group? So firstly, dipole moment, two electrical charges of opposite sign and equal magnitude separated by distance. This is a vector quantity, and what it does is establishes what's known as an electric dipole, or charge separation. As it's a vector, it has direction. And so a good example of this is the polar molecule water. So water has two lone pairs, which aren't shown on this diagram, and it has a bent structure. But because of the polar nature of the oxygen-hydrogen bond, we have a bond dipole. So the bond dipole exists between oxygen and hydrogen. Oxygen is delta negative, hydrogen is delta positive. That's what the vector shows, arrowhead pointing towards the more electronegative element. So we have two bond dipoles, and because of the asymmetric arrangement of these bond dipoles, that is, because they're not directly opposite one another, we have a dipole moment. So a dipole moment essentially is the same as a polar molecule. So water has a permanent dipole moment, and so it's considered polar. Now, if you have a look at these other molecules, well, we've already looked at water. Two polar bonds. The vectors are showing that. The two vectors pointing towards oxygen. But because of the arrangement, there's a permanent dipole moment. So water's polar. Same with fluoromethane. The carbon-fluorine bond is very polar, and so it's a permanent dipole. If we look at carbon dioxide, we have two polar bonds, bond dipoles, if you will. But if you look at the arrangement, they are essentially pointing in the opposite direction, separated by an angle of 180 degrees. So there is equal pull towards both oxygen. Therefore, these bond dipoles, which after all are vectors, cancel out. If we added those two vectors, the sum of those vectors would be zero. Therefore, the molecule is non-polar. And we could say the same for tetrafluoromethane. Four very polar bonds, but because of the arrangement of these bonds, that is, symmetrically around the carbon atom, all the bond dipoles cancel out. And so this is a non-polar molecule. There is no dipole moment. Because of the arrangement of the bonds, those vectors cancel out. So I'd like you to understand three types of intermolecular forces: hydrogen bonding, dipole-dipole force, and London dispersion force. And you may have heard of some of these, if not all of them. So hydrogen bonding is when you have a hydrogen atom bonded to one of nitrogen, oxygen, or fluorine. Hydrogen bonded to NOF. And this is, relatively speaking, a large difference in electronegativity. Therefore, it's a large bond dipole. And so it does have the capacity to be quite strong. Hydrogen bonds can be considered the strongest intermolecular force. A dipole-dipole force, on the other hand, is due to the asymmetrical arrangement of bond dipoles, so these polar bonds, but this would not include any polar bonds that are made up of hydrogen bonded to nitrogen, oxygen, or fluorine. If you have that situation, those are hydrogen bonds. But if you don't have that, they are just considered dipole-dipole forces. Finally, London dispersion forces, or shortened to LDF. This is based on electrons, and so what we have with LDFs is an asymmetrical arrangement of the electrons in the molecule. And what this leads to is short-lived but weak forces due to this arrangement of electrons. In terms of strength of these intermolecular forces, hydrogen bonds are the strongest, London dispersion forces are the weakest. So here is hydrogen bonding. So once again, we'll start with the water molecule, and we want to look at two parts of this diagram. First of all, the oxygen-hydrogen bond in a molecule. That is an intramolecular force of attraction. Intramolecular forces are between atoms within the same compound, within a molecule, or even within an ionic compound. So you need to think chemical bond for intramolecular force. On the other hand, we have this particular dotted or dashed line, and this is representing an intermolecular force of attraction. So there's a distinction intra, between atoms of a molecule, whereas intermolecular force are forces of attraction between neighboring molecules. So not within a molecule, but between molecules. It is these forces that get broken when a substance changes state from, say, liquid to gas. If you look at these types of forces in the context of organic chemistry, here's a molecule of ethanol. So ethanol has a carbon-oxygen hydrogen bond. Well, the oxygen-hydrogen bond is the bond of specific interest because that is that specific type of dipole-dipole force, and so it's called a hydrogen bond because it's hydrogen bonded to oxygen. And so the hydrogen bonding between alcohols can be quite strong, and that is due to the OH bond dipole of the hydroxyl group. This is a pretty strong intermolecular force, and so alcohols typically have relatively high boiling points. It's hard to break apart those molecules because of the hydrogen bond. This is a carboxylic acid, and notice carboxylic acids such as ethanoic acid also exhibit hydrogen bonding. We have the hydroxyl group on a carboxylic acid, and so because of that hydroxyl group, you have establishment of hydrogen bonds between neighboring molecules of ethanoic acid. It's between. That's why you want to remember. It's about breaking forces of attraction between molecules. The second type is a dipole-dipole force, and as mentioned, this occurs in any polar molecule. Hydrochloric acid, or HCl, is a polar molecule. It has a permanent bond dipole, therefore it has a dipole moment, but it's not hydrogen bonded to nitrogen, oxygen, or fluorine. So we do not get hydrogen bonding in hydrochloric acid. That said, there's clearly still a force of attraction between two molecules, and that's shown in the bottom part of the diagram. And because the force of attraction is caused by a dipole moment in the two molecules, it's known as a dipole-dipole force. And so dipole-dipole forces occur between any two polar molecules. Any two molecules with a permanent dipole will show dipole-dipole forces as their intermolecular force. Here's another organic molecule. So this is an ether, And so this ether has has a dipole moment, and that dipole moment exists because of the asymmetrical arrangement of two bond dipoles. The carbon-oxygen bond on either side of that oxygen is a polar bond. They're not arranged symmetrically. Therefore, for methoxyethane, there is a permanent dipole. And so the force of attraction between these two molecules, the electrostatic force between the positive component of the dipole and the negative component of the dipole, would be known as a dipole-dipole force. And so this dipole-dipole force exists in an ether, but it's not as strong as hydrogen bonding. So we would expect ethers to have a lower boiling point than something like ethanol. Here's another example. So this is an ester. Can you figure out the name of that ester? That's right, ethyl ethanoate. And so if you look at this molecule, it actually has two different dipole moments. The carbon-oxygen-carbon bond is polar because of the arrangement of the oxygen atom around those carbons, and the C double bond O is also a polar bond. And so we have two different dipole moments, therefore two areas for establishment of dipole-dipole forces in an ester. So esters have, relatively speaking, higher boiling points than anything with simply LDFs. The final one, London dispersion forces, as was mentioned, is due to asymmetrical arrangement of electrons in the electron cloud. And so this image is trying to show that. If you look at the image on the left, 3 electrons equally spaced, there is no polarity associated with that atom. However, if somehow the electrons arrange themselves as shown on the right, you have polarization of the atom. That is a delta positive and a delta negative component. As soon as you have that, you have the possibility of London dispersion forces of attraction with neighboring atoms that are similarly polarized. So here's an example of 3 hydrocarbons that exhibit the change in London dispersion force. Methane to ethane to propane to butane. And so the strength of the London dispersion force increases from left to right. And what's the reason for this? Well, the reason is each subsequent molecule from left to right has a larger electron cloud, which gives a greater chance of polarizing that electron cloud. If there's a greater chance of polarizing it, it will polarize more, and you will establish more and stronger London dispersion forces. They're still very weak, but you just get more of them as you get more electrons being present. Here's another example, 2,2-dimethyl propane, which, if you think about it, is almost like a ball, and then pentane. So a 5-carbon pentane chain, which is more like a stick. And so which one would have the greater boiling point? Well, pentane does, because it has stronger London dispersion forces. And why are the dispersion forces stronger? It is because pentane has a greater surface area, meaning there's a greater possibility of establishing London dispersion forces along that chain. With 2,2-dimethyl propane, which is essentially spherical, there's only a few points of contact for London dispersion forces. So here's a bit of a summary. First one, ion-ion force, ionic species, and you could add covalent if you were talking about nucleus force, but those are intramolecular forces. They're typically very strong, but they're intramolecular, not intermolecular. So we have hydrogen bonding, which of the 3 intermolecular forces is strongest, and we will see these in alcohols, carboxylic acids, primary secondary amines, and primary secondary amides. finally, secondly, dipole-dipole ketones and esters with that carbonyl group. C double bond O is polar. Alkyl halides will also potentially have a dipole moment. And then dispersion forces, anything that has no polar bonds will exhibit dispersion forces. Everything exhibits dispersion forces. However, the shape and the size of that molecule are going to dictate what they look like.